I've got the pleasure to announce the last presentation in this track for today, which is given by Thibault Kuntzer from Identitas. He's talking about data-driven animal health and welfare metrics for livestock farming. Thibault works as a data scientist to promote the use of advanced analytics in animal data. The Smart Animal Health Project is a joint initiative of the Swiss Federal Food Safety, the Veterinary Office, and the Federal Office for Agriculture, aiming to find new data-driven metrics by combining the data and thus improve the monitoring and support of livestock care. Thibault, we're looking forward to your presentation about pigs, cows, and chicken.
Thank you. Thank you very much. Hello, everybody. So the livestock farming sector is a very well monitored field in Switzerland. Farmers care for their herds and they have to register all of the major events in the animal life. Veterinarians control the population and make sure that the animals stay healthy. Independent bodies control the farms and the holding conditions to make sure that they follow regulation. This data trove can be mined to find new animal health and welfare metrics. And this is what I'm going to talk about today, the Smart Animal Health Project. I will start by introducing the livestock sector in Switzerland and its monitoring activities, and then I will make the case for data-driven techniques in this sector. I will then briefly talk about the Smart Animal Health Project, and I will delve into the data science aspect of it with two examples, the first one being data validation, and the second one, data-driven health risk index. All right, so let's go to livestock farming in Switzerland. Let's restrict ourselves to only cattle farming. I will broaden the view at the very end to other species, but for now, let's focus on cattle. There are about 1.5 million cattle distributed over 37,000 holdings in Switzerland, which are doing dairy and beef production. So the livestock farming is a subsidized and highly regulated field, amongst which the health and welfare of the animals are a key priority. All of the animals can be very well traced from their birth to the end product, and the farms and the holding conditions are controlled by independent bodies. And the results go into monitoring databases. So we have the farm details, we have the traceability database, which lists animal profile and their history. We have the results of the farm controls and of the veterinary controls. All right, so why should we use data-driven methods? Well, we can do early detection of systematic problems. We can also better target the inspections to foster health and welfare. And of course, we can assess the long-term health trend of the animal population. So the case for data-driven methods is very strong. And this is exactly what we want to do with the Smart Animal Health Project. It's a data-driven monitoring of the livestock population, or I should rather say populations for the different species. It's a large public-private consortium funded by the government, the Office of Veterinary Affairs, and Office for Agriculture. And we are 12 research partners in the academic world. We have also livestock organizations and private companies supporting the livestock sector. I really like this project because it's a complementary approach. We have the data analysis, and I will focus on this data analysis part, of course, but we also have a group thinking about the future of data collection, and another doing field research and validation of the tools we do by veterinarians directly. All right, so let's go to the data science aspect of it and talk about data validation. In our databases, most of the data are entered by humans, so it means that they are prone to human errors, of course. Here is an example of a part of the animal profile that we have in your traceability database. And if I were to give you the task of validating those data, then you could say, okay, the animal must have a date of birth, Okay, but then you quickly think that maybe if it has a date of death, then this one should be after the date of birth. It's logical. So the list of conditions for this rule-based approach is immense and growing very quickly in complexity and simply in length also. So we are investigating another approach, and this one is based on autoencoders. So unsupervised machine learning for anomaly detection. What we have is the input data that is projected into a smaller space. This is the encoding part, and then you have the decoding part, which projects this back into the data space. And the algorithm learns the identity function. So the reconstruction data must be very similar to the input data. If you have big errors, it is that something went wrong. Either it's the training, but this would be for all of the data points, or that some of the data are outliers that were not represented during the training set. So you can remove those from your data set. So you get a cleaner data set. You can do this iteratively to remove simple errors, like I forgot to enter the date of birth, to more complex errors. Here are two real examples of the anomalies we've detected with this system. You can see on the first line, it's missing its breed, the sex, and the date of birth. As a human analyst, I would clearly put this as the cause of the anomaly. On the second line, you see that this Simmentaler bull is more than 40 years old. And this exceeds greatly the lifespan of this type of animal. So clearly, either the date of birth is wrong, or it's missing the date of death. The neat part about this algorithm or this model is that you can compute the reconstruction error on a feature at the feature level. So you can compare and see which feature is contributing the most to the errors. And if you do this for those two cases, you see the first line is it's indeed the breed, the sex, and the date of birth. And for the second line, the date of birth is considered wrong. All right, so we did an unsupervised anomaly detection. We've discovered simple anomalies, like say I missed the date of birth, or very complicated cases. For example, the weight at birth was wrong for this breed and this sex. So this is already something very complicated. We had to do also data augmentation. For example, for the stillbirth, those were considered outliers. And the stillbirth for the cattle population is about 2 to 5% in the population. And if you don't do this data augmentation, this means you don't increase the frequency of those data points or those examples in the training set, then they will simply be flagged as outliers. And you don't want to do this, at least in this case, because stillbirth is sadly a correct entry. This code or this model is currently slightly past the proof of concept stage, so we still have to improve it in order to deploy it in production, but that's something we are aiming to. I want to highlight the fact that this idea was inspired by this very conference last year by the talk of the people over at InCube. All right, so let's leave the realm of unsupervised machine learning and go to supervised data analysis. We want to do a data-driven risk index. So in order to control risky farms more often, we work for the development stage. We've pseudonymized the data in order to protect the privacy of the farmer and the farmers. And the key question is it possible to predict the farm control results? For this, we have a lot of data. We have all of those monitoring databases. Of course, we have the traceability database. It's about 6 million notifications per year. There you have the animal profiles, and you have all of the events in the animal life. You also have the farm details, where you can find the location of the farm, meaning which canton or which type of terrain it's in, and you also have the type of farming. You have also the label membership. Does it belong to a program for animal security, for example, or animal health? And what we want to predict is the results of the farm controls. But we wanted to do something simple, so instead of making a complete prediction of this farm will fail on this or this precise control point, we want simply to predict the incidence of deficiencies. Or even simpler than this, whether it's a farm with a low rate of deficiency or a high rate of deficiencies. So it's a binary classification in the end. So what we've done is to use a very small training set with about 2,000 data points, and this one is balanced. So it's very nice because we don't have to use fancy unbalanced techniques. We've tried. We can use an unbalanced training set because there are much more good farms than bad farms, if you want. So this is already good. But if we do this training with an unbalanced training set, then the results are not much better than with this simple balanced training set. We have about 200 features for now. If you list all of the possible features that you get from the monitoring databases, this number gets high very quickly. So at some point, you want to do feature selection and feature engineering. A key aspect for us and for all of the partners involved in this project is to be able to explain what's happening, what are the predictions. Why is my farm worse than my neighbors? This is also, of course, very important, both for the acceptance of the model and the acceptance of the controls, or the legitimacy of the controls. So we built simple models and more complicated ones. We tested those and we get high accuracy and F1 score, which means that we can predict with high confidence whether a farm will be at risk of a health problem in the future or not. What we have observed also is that simple methods, such as linear support vector classifiers, work not much more worse than fancier methods, like, say, random forest or neural network classifiers, which is very good for us because we want to explain the decision that the model took. What are the next steps? Because it's not finished, it's never going to be finished. We want to integrate more data sources. And we want to do better feature engineering, better feature selections. So it means that we have to talk with the group that is doing the data, the metric validation on the ground. And also we have to talk with the group doing the data collection. They can then say, okay, this feature is for us data scientists predicting the health and welfare of animals not relevant. So this is very nice because if we are missing something, we can request it. It doesn't mean that we will get it, but we can request it. And of course, we want to expand this to other species. This talk was mostly about cattle, but we can think about pigs or a lot of other animals. This is the Smart Animal Health Project. It's a data-driven monitoring of the livestock health and welfare. It's a population-level approach, so it means that we are looking at the whole population and not at the individuals. And it's a very complementary approach between data science, the future of data, or how we do data collection, and field work. So I thank you very much, and I guess I'm open to questions now.
Yes, thank you very much, Thibault. It was quite interesting to see what's possible today, and yeah, wondering what's possible in the future. But first, some questions from the audience. The first question is, can you explain in more detail what risky farm means? This is which parameters actually applied to make them risky?
So I said at the beginning that the livestock sector was highly regulated. So it means that we have a whole list of criteria. For example, the size of the holding, the light, do the animals have access to the exterior and stuff like this. So, and the control results will show whether those points were actually met or not. So we have a very well-labeled training set, if you will, because it's done by humans controlling farms every day.
Okay, so we're talking to experts before...
We are talking to experts, yeah.
Okay. And the next question is actually, you said that data is entered manually.
Yes.
Who is entering the data?
Well, you have the farmers, so each time they are moving an animal from one farm to another, they have to say that they are moving the animal, so they register themselves that the animal is moving. So this is the part for the traceability database. Of course, this is controlled by independent bodies, but still it's the farmer that enters the data. And for the others, it's either the regulator. So if you go on a farm and you control this farm, then you enter your result in the database, and the veterinarian also enter their own results.
Okay, so how do you motivate the farmers to enter the data? Is this a regulatory task they have to do?
And they get some money also out of it.
Okay.
And if they don't, they also have to pay a small fee.
A penalty.
A penalty, yeah, exactly.
Okay.
So it's very motivating, yeah.
It's very motivating. I can imagine that. And do you use data from outside Switzerland? Are there actually international examples who doing similar projects?
Livestock farming is in Switzerland. It's very special. I mean, we like our cows. I mean, they are everywhere on all pictures. So it's slightly different, and I mean the details are slightly different. The controls are slightly different. So until now, I haven't found an example of a similar project. We are going in this direction of the digitalization of agriculture with IoT. You can replace the traceability databases with IoT and then get this automatic traceability. But for now, I think this is a very one-of-a-kind approach. Yeah.
Okay, yeah, that's what I was thinking. The future of data collection might be that all the animals are actually chipped and sending.
You might have health issues because those are heavy, and they can the animals can get hurt with those IoT. So it's difficult.
The bells are also quite heavy.
I'm sure we'll get there.
Not heavier than the bells, right?
Oh no, it's small plastic thingies that
That's what I thought, because that's a discussion as well, whether the bells are actually difficult for the health.
They are, yes, and they're causing health problems as well. And they're trying.
You do know that?
Yeah. It's a very interesting field. I mean, you learn quite a lot. Yeah, definitely.
Okay, that's great. So thank you very much for the insights on the health data in Swiss cattle. Quite an exceptional topic, but very interesting what can be done with data here. So thank you very much, Thibault, and have a great evening. Thanks for coming.
Thank you.